So I see mostly Japanese student, right? Okay, you're very on time. Is a very good habit. Okay, so for me, I think usually the summer course should be like more relaxed. Okay, so I don't want to give you much loading for that. Okay, so today's class is a general introduction. Okay, of some of the properties of material because I belong to the Department of Material Science and Engineering. Okay, my name is Meng Lin Cai. Okay, I'm currently an associate professor in the Department of MSE. Okay, so for the first 1.5 hour, okay, I will explain some of the. I'm not sure your background. Do you all come from the Department of Mechanical Engineering? Is there? I mean, for the Japanese student, is there anyone from the material science? Oh, okay, very good, very good. Okay, so most of my topic comes from the material science textbook and or some physical properties of material, but I'm not gonna cover the topic of mechanical properties, okay, because I think like most of you have already gone through that, okay, during your undergraduate studies, okay, and I also know that on Monday you're going to TSMC, right? Okay, so maybe I will give you some brief concept of the semiconductor. Okay, semiconductor. What do we do in the semiconductor industry? Okay, but not maybe not related to your project. Okay, but later on, maybe after this course, you can write down some recommendation what we can do to incorporate the project with like for example the other properties of materials. Okay, so for example when they ask me if there's anything we can do to add some material in your soft robot, right, I said like maybe I can add some quantum dot to make it fluorescent. Okay, but since you're usually the quantum dot are like not very high concentration one, okay, so we'll need a lot of quantum dot, so it will be very costly. Okay, maybe you can like all come up with only one prototype. Okay, so this time we did not include it. Okay, but for the second part of today's topic, I will invite. We arranged another, I think, PhD student from Professor Zhang's lab. Okay, their lab is very focused on the uh, fabrication of piezoelectronic devices or the triple electronic nanogenerators. Okay, so um, it was originally arranged that Professor Zhang will come himself, but since he has a meeting to attend, okay, so his student will come to offer that course. So for the second half of the this morning's course, okay, it will be more related to your project, okay, but I'm just gonna give you a general introduction, but I will go to describe the homework first. Okay, it will be a very easy one. Okay, name one of the most interesting material properties you have heard before. Okay, use 100 or 200 100 to 200 words to briefly explain the underlying concept of the properties. Okay, so it will be graded depending on how interesting the material properties is. Okay, so maybe you have heard that something like thermoplastic materials, okay, or superconducting behavior. Okay, you can briefly describe the the concept. Okay. So I think this is will not cause you any trouble, and I include like over 100 pages, but I will like skip some of them. So the slide may be for your information. Okay, so my research currently based on the synthesis or growth of nanomaterials. Okay, so for one part of my group working on the synthesis of quantum dots, okay, especially what we call the halide perovskite quantum dot. And the point for the quantum dot is to do some light conversion behavior. Okay, later I will spend some time to show it. And also, I try to grow some 2D material. 2D material means the most famous one I think is graphene, right? You use the Scotch tape to exfoliate graphene from graphite, okay, to make it atomically thin layer, right? But our group focus on the growth of semiconductor 2D materials, okay? So try to develop some 2D electronic devices such as field effect transistors, okay, and try to explore the underlying mechanisms of these devices, okay? And I also done some like e-beam lithography or solar cell research during the past, okay? So this is a brief introduction of me. And then this is my CV, okay? So before we start, okay, let me briefly introduce the Taiwan Tech, okay? So it's founded in 1974 and it's actually a relatively new university. And in 1982, we started the PhD program. Okay, in 1997, we renamed because originally it's just the National Taiwan Institute of Technology. Okay, for some student coming from like a vocational high school, usually we have two types of vocational high school. One type is 3 year, one type is 5 year. Okay, so for 5 year, the Institute of Technology provide 2 years of study, and after that you get the bachelor degree. Okay, but for 3 year we have 4 year of study, and after that you get the degree. Okay, so I think you all know this located in Taipei, and then I think you live in for the Japanese student you stay in the Huaxia district, right? Huaxia campus, right? Okay, so another dormitory. So we just merged that university. Okay, so like 2 years before. Okay, and that belongs to the New Taipei City. New Taipei City is the surrounding the Taipei City. So the area is actually larger and with even more population. Okay, so if you have time during like your stay, you can like try to explore around. There are some vendors or some food, or okay. So I think there are a lot of food around there. Okay, some of them are local restaurant. Okay, some of them are from like a Southeastern Asia style. Okay, so currently we have the most international degree student in Taiwan. Okay, so mostly comes from like 65 countries, and mostly from Indonesia, Vietnam, and also some from Ethiopia. Okay, so this is a brief introduction to say that we are very internationalized. So there are a lot of English courses offered in English. Okay, and this is the college overview. So we belong to the College of Engineering, and this course composes of students or lecturers from the mechanical engineering and the material science and engineering. Okay, and there are some research centers. I will just skip this part. This is more related to research. And then I think you use the high-speed 3D printing research centers resource. Okay, so I want to mention that. Okay. Okay, so I want to spend some time to talk about the international internship pilot program. Okay, so if you're interested in the future to come to Taiwan to do a short-term internship program, this I think usually is a very easy one. Okay, and our university actually provides the dormitory. I'm not sure whether you need to pay for that. Okay, maybe it's like a half sponsored, half on your own. Okay, and then this internship program lasts for like 3 months. Okay, lasts for 3 months. Okay, and each month provides NT $30,000 for the internship. Okay, so it's about like 100,000 Japanese yen. Okay, And for each month, you only need to write a short report for that. Okay, so if you're interested to explore more, okay, especially maybe like the night market or shopping mall, okay, you can or the attraction sites. Okay, so you can consider that. Okay, the duration for the internship, because this is all information. Okay, every month they will renew it. Okay, so if you interested, you can check it out. Okay, and I think our university is quite convenient. Okay, near the MRT, so it's easy to explore around. And for this type IIPP, I think the dormitory will be offered in our main campus. Okay, and these are the professors offering the opening positions. Okay, for the internship program. Okay, so mostly from the engineering college of engineering. Okay, some of them from our department, some of them from the mechanical engineering department. And I don't see my name on top because I after I see this slide, I add my information. So at that time I wasn't a part of the program, but now I joined. Okay, and briefly introduce our department. Okay, so originally it was like a traditional style. Okay, we called textile engineering, fiber engineering, and 2003 we changed to polymer engineering, and 2010 it becomes our current name. Okay, so after we changed to 2010, we hired some professors from the inorganic material background. Okay, including me. Okay, but actually for nanotechnology, sometimes we need to incorporate inorganic with organic solvent, organic ligand, organic compound. Okay, so there's still some collaboration between the professors from different background. Okay, so for the second hour, the PhD student will be coming from the polymer engineering division. Okay, so more related to you have done with in your project. Okay, soft gels, soft robot. Okay, so I will skip this. This is just say that we have almost 30 professors. And these are the overview views of the professor research fields. This is just for your information. Okay, maybe later in your career you want to explore some various type of research fields. You can know like who you can contact. Okay, who you can contact. Okay. So we have professor working on like organic electronics, biomaterials as organic simulation, and also cancer biology. Okay, and also energy or like a battery materials. Okay, organic electrical devices. Okay, and we have also some professor working on LED. Okay, patterning of LED. Okay, patterning of LED to to tune the light performance. Okay, because the structure on the LED will change your light profile. Okay, you want to make it more collimated, or you want to make it like a spread wider angle. Okay, and we have professor working on functional polymers. Okay, and for the inorganic division, okay, we have professor working on metallic materials. Okay, metallic glasses, and also some electrochemical catalysts. Okay, and thin film and metallurgical thermodynamics. Okay, and so on. Okay, and we have this is our chairman working on ceramic material. We have a professor focus on the electron microscopy, and we have professor growing nanowires. And this is me. Okay, I like playing tricks. Okay, or like so I dress up like that. Okay, so it's not quite important. Okay. So these are our public labs. Okay, mainly in material science, you will see some microscopes, but usually not optical microscope, okay, usually electron microscope, so that you can see nanoscale. You can achieve the nanoscale resolution, right? Or you can go to atomic scale. You can see the atoms using, like, for example, the high resolution transmission electron microscopy. Okay, and you can also do some cutting. Okay, you can cut at the sample using focused ion beam. Okay, you can use focused ion beam, and you can do some characterization of your crystal using XRD, right? XRD. So these are the tools that we usually use in our department. Okay, so we actually also have a 3D printing lab. Okay, I think 2 years or 3 years before, okay, this summer course is also supported by the 3D printing lab. Okay, and this is actually you can see many 3D printers, because this is a national qualification lab. Okay, so if you want to qualify, you can like apply and then you get the license. Okay. Okay, so now let's go on to talk about material science. You can see that for different Coca-Cola bottles, what are the difference? Okay, what are the difference? Which one is the best? I personally like the aluminum can. Okay, because you can see that usually for the aluminum can, the gas in the Coke is sealed better, okay, than the other types. Okay, I think the worst one is the PET one. Okay, usually after you open it, you need to drink it very fast. Okay, otherwise it will be very disgusting. Okay, because it will become no gas, only the like a sweet water. Okay, something like that. Okay, so the difference between them are what? The first one is the metal, right? The second one is ceramics, and the third one is polymer, right? Polymer material. So you can see that in material science, we can try to use different kinds of material for similar application, right? Similar application. And each one has its own benefit and disadvantage, right? Maybe for this one, cost more, right? And for this one, the bottle itself is more cheap, okay? Or we can, if we reduce to the nanoscale, you can see that on the right here, these three, what's the difference? They all made from carbon, right? They all made from carbon. So what's the difference? For this one, it's planar, right? It's planar. Okay, so you can see that this is what we call, if you know some basic chemistry, is like a sp2 orbital, right? Okay, sp2 orbital. Or you can try to what? Make it into a tube, right? If you try to bend it, okay, and attach one side from another, it becomes a tube. Or you can make it like a sp3 orbital. You become the diamond, right? So what's the main difference? The big difference is that graphene, we usually call it a metal, right? A carbon nanotube, depends on it's a single wall or multi-wall. It can be a semiconductor. The conductivity, it can actually be tuned. Okay, and diamond is what? Is a very precious jewel, right? Precious jewel, and it's an insulator, right? Is an insulator. So by different atomic orientation, you can actually change the properties of materials. Okay, so that's what material science is about. Okay, we try to use the same element. We try to make different orientation. We try to make the different thickness or different applications, to achieve different application. Okay. So this is the structure of what we said, this body center cubic, right? Okay. And for example, for some steel means iron carbon material, iron carbon, you can say compound. Okay, when you increase the temperature, the structure may also be changed. Okay, sometimes it's a body center cubic, sometimes it's face center cubic. And for different structure, what can you achieve? You can achieve different mechanical properties. Okay, because from one atomic position to another atomic position, the distance changes. Okay, and sometimes the structure change also give to the electronic change. The electronic properties, more conductive or less conductive. Sometimes the optical properties change. Okay, for example, if you have like a zinc and the copper, zinc and copper alloy, okay, for different structure, the color of the zinc copper, we can say that the brass, okay, brass, the color of the brass changes. Okay, and one thing quite important in material science is that defect is one of our focus in our study. Why? Okay, you can say that if you imagine the semiconductor industry, how to make different type of semiconductor, you have heard like a P-type or N-type semiconductor. Actually, these are all defect. So sometimes defect is not always bad. Okay, you need to apply some defect in order to change the properties of material. Okay, so for example, for silicon, if you add like a gallium, because gallium has one additional valence electron. Okay, so it will give you N-type because you have more electrons in your crystal, right? Okay, if you add boron, you will become like P-type because you have a positive vacancy. Okay, you can say positive vacancy or some void or some open space, right? It means that it's one electron less than other atom. Okay, so give you a P-type semiconductor. Okay, and also we try to evaluate the mechanical properties and failure. We try to, the failure usually not only consider the structure. Sometimes you need to consider the environmental effect. For example, salt in water can act as catalyst to induce what? To induce fracture. Okay, fracture. And also, if you have an airplane, okay, flying over around in the sea, on top of the sea, the salt concentration will also be increased. So it will also induce the failure. Okay, and also some processing technique. Okay, so how to make a ceramic or glass Coke bottle. Okay, we try to use like a hot pressing, blowing, or some other technique in order to form that structure. We need to come up with a mold. This is more like what you did in the soft robot, right? First, you need to design a mold, and then you need to try to process it under a certain temperature, right? Certain temperature is good for forming. Okay, good for forming. So after you place the AB gel in your mold, you need to process it to make the form. Okay, and eventually you want to like cool it down. Okay, to make it a rigid object. Okay, but for polymer is relatively different. Okay, because you try to make it rigid after placing in a certain temperature, high temperature. Okay, so it's relatively different. Okay, and also some properties of material we try to study in material science department are like electrical behavior, magnetic behavior. Magnetic behavior is very important in the design of electronic microscope, because for for optical microscope, you use optical lenses, right? Okay, you try to form a glass, you try to polish the glass into a shape that using the refraction of light, you make the light to converge, right? And of course, different light has different wavelengths. Different wavelengths, the focus point will be different, right? However, in electron microscope, the source is not light, it's electron. Okay, so how to converge the light, make it focus? Okay, you need to use electric field or magnetic field to change the direction of electron. Okay, so the magnetic behavior is also important, and also the optical behavior. Okay, why some light is blue, some light is blue, red. Okay, because different material provides different band gap, and the band gap is actually, you can think of it as one electron, you have different orbital. But if you have a crystal is the periodic orientation of electron, the certain energy level becomes a certain region, okay? Or you can say certain band, okay? And the band to band difference provides what? Energy difference, right? The energy difference, the level of energy difference will give you what? If it is the energy level difference corresponds to a certain wavelength, the light wavelength corresponds to the energy. Okay? So by tuning the band difference, you can tune the emission light. Okay, the color of the emission light. You can even go to like an ultraviolet or go to infrared. Okay? And also the thermal properties, how to protect, how to prevent the thermal damage in your product. Okay, is also an important task in the physical properties of materials. Okay, and these are the material characterization techniques. Okay, we try to use the transmission electron microscopy to, first of all, because myself working on quantum dot, right? Quantum dot means nanocrystals. If you want to know, nanocrystal means you have a material with the side length less than like a 100 nanometer. So how to observe that? You cannot use the optical microscope, so you need to use transmission electron microscope. Okay, so after you prepare your sample, you can see that the distribution, you can even make a distribution profile, like a 10 nanometer, how many? 20 nanometer, how many? Yeah. And other than that, you can try to use, you can see that TEM here, you use electron as a source. After passing through a periodic structure, what will happen? Okay, if you have a light passing through a grating, you will experience something called the interference or diffraction, right? Okay, similarly, if you have an electron passing through a periodic structure, it will also give you a diffraction pattern. Okay, of course, you need to make your sample very, very thin in order to achieve the diffraction pattern. Okay, and what can you get from the diffraction pattern? Okay, for light passing through the grating, if you know the distance, if you know the wavelength of light, okay, you can try to evaluate the grating period, right? The width of the grating, because it can be calculated. Okay, I'm not going to go into detail. I just want to give you the concept, right? Similarly, for electron microscope, you can get the wavelength of electron. Actually, it sounds weird. What's the wavelength of electron? Okay, because the electron, the applied voltage of the electron will give you an acceleration speed, right? The acceleration speed give it a certain energy. The energy can be calculated into a certain wavelength. This is called the particle wave duality nature of electron. Okay, even for ion, you can calculate the ion wavelength. Okay, for electron, you can calculate the electron wavelength. The only thing you need to know is what? The acceleration voltage. Okay, if you know the acceleration voltage, you can convert it into wavelengths. And after you know the wavelengths, you know the diffraction pattern. And also maybe you know the distance between your sample, your phosphor screen and your sample. You can try to evaluate what? Your atomic distance between your crystal. Okay, that's how we try to analyze our material, right? By getting the diffraction pattern, you can know what? The distance between your plane. The plane means the plane oriented by what? By your atoms. Okay, so we don't usually use the distance. We don't usually only use two lines here, what we see. This is called a direct observation. Instead, the more accurate way is you go from the diffraction pattern back, okay, to your plane distance, okay? So that's how TEM works, okay? And also, scanning electron microscopy, I think most of you may have known that by detecting the electrons emitted from your sample, you can get the surface morphology, okay, of your material. Okay, and X-ray diffraction, you can know this is similar as the electron diffraction. Okay, instead, X-ray is a very transmittance, the high transmittance light source. Okay, for TEM, you cannot make your sample very thick, because if the sample is too thick, the electron will not penetrate through. Okay, but the X-ray has high penetration. Okay, so it's good for what? Large crystal analysis or powder analysis. Okay, powder analysis. You can try to get the diffraction peak. The diffraction peak here, what's the use of that? From this, you can calculate back because you know the wavelength of your X-ray, right? And then you know the angle. From this, you can calculate back to this crystal structure. Okay, so one thing very important in material science is we try to understand the crystal structure, and using the crystal structure, it can be used as the DNA of your material, right? So you can identify, this is the material I want, this is not. This is the material, maybe similar to our material, but maybe we can try to adjust the crystal structure, okay? And for 2D material, if we have a very thin material on top of a surface, right? We can use the scanning probe microscopy to scan, okay? To scan. It will give you a high profile, right? Okay, the high profile, the resolution can be as high as like a 1 nanometer. Okay, so for example, for graphene, okay, you can try to use the scanning probe. Scanning probe means you have a tip, okay? When tip interact with your surface, it will generate the electrical signal to what? The high profile. Or you can do mapping, but this takes time, okay? You need to scan like a 1 by 1, okay? And if you want to get very clear image, you may take like 30 minutes, 20 minutes. Okay, and if you have two type of material with the same height, okay, for example, both material 1 nanometer, okay, but there are two materials here. For 1 mole, this is a simple mole, okay, you can say this is a simple mole. For 1 mole, you can only get like a 1 height profile. So you think this material is the same. Actually not. Why? Because for scanning probe microscopy, you can use some AC current, AC electro signal to make it like a tapping mode, okay, or AC electrical mode. Okay, so for that, you can see that we also scan here, right? But you see, there's a dark region surrounding the bright region. Okay, this provides what? The information for different material. Okay, so you can see these two material has the same height. Okay, but they are composed of different material. Okay, the outer part here is maybe the MOS2. Okay, the inner part here is the WS2. Okay, so this is the one of the advantage for the scanning probe microscopy. Okay, usually you will hear like AFM, okay, atomic force microscopy. Okay, but actually AFM is just one mode. You can try to use some magnetic tip to evaluate like a ferromagnetic ferromagnetic thin film, or you can use like a piezoelectric tip, okay, to evaluate your piezoelectric material. Okay, so there are different modes you can apply in the scanning probe microscopy. Okay. Okay, so one thing important in the material science is actually many material techniques related to the semiconductor processing. Okay, so for example, these three are all field effect transistors. Field effect transistor is the building block for your like a CPU, okay, your memory, not your memory in the brain, the memory in your electronic device or laptops, cell phones, something like that. Okay, so usually in material science department, we only do very essential devices such as field effect transistors, or even more easier is the like a diode, PN junction. Okay, if you want to go to very complicated design using commercial materials, you will go to like a double E department. Okay, double E department, they use like a mature material to make complicated design. Okay, but in material science department, we usually use new material to do simpler design. Okay, but because we all need new materials, okay, we all want to explore new materials that can replace the current technology. Okay, so it's also quite important. Okay, so for the device design, since when you reduce the electronic device, the size of the electronic device, you will encounter some problems such as the current leakage problems, short channel effect, right? So in order to prevent, to control your device better, people try to like change the planar FE2 to FinFET. FinFET means we have a gate surrounding our channel. Okay, the gate surrounding our channel can make better control to prevent the leakage from one side of the transistor to the other side. We usually call it source and drain, right? Source, drain, and gate. Okay, and for the next stage, people try to even better control is like surrounding on full side. Okay, full side is called a gate all around. Okay, so currently the technology is like a FinFET, but many semiconductor companies such as TSMC, Samsung, and Intel, they all provide some solution for gate all around. Okay, however, the yield rate, okay, is still not quite good. Okay, so it's still challenging. So now, if you now go to the semiconductor industry, maybe you will try to produce some product with FinFET, produce some product with gate all around. But in the textbook, we usually still only see the planar FET. Okay, and also apart from the device design, okay, the packaging is quite important. Packaging, what's packaging? In the semiconductor industry, we don't only consider semiconductor. If you only have semiconductor, your laptop, no use, okay? You always need some interconnect between your devices. Interconnect made of what? Metallic wires, right? And also you need some insulating layers, okay? They are like polymers or oxide to what? To protect your inner circuit, right? Otherwise, you have like an oxygen react with your wire, okay? And it breaks apart, or it becomes an insulator with no use, right? Or you put it in water, okay? And it becomes like a react with some ions, okay? And it disappears, also no use, right? Okay, so the packaging techniques is also important, okay? So traditionally, we have 2D packaging. Like we have one, you can imagine like a one PCB or one wafer. Okay, you have A region, B region, C, D, E, right? And then if you want to connect one from to another, you need to have a long global wire connecting between them. Okay? You can think of it as this is the one field effect transistor. But here, each region composed of like several tens or hundreds of transistors. Okay? For example, if you want to come up with a memory, right? Maybe you need like several hundreds of field effect transistors in order to do that. Okay, that means this is called some logic design. Okay, you connect one from another, it takes very long time. Okay, and also your current will dissipate during the transmission, right? So now, when you try to reduce the size, what can you do? Okay, we go from like 2D to 3D packaging. Okay, 3D packaging is like you try to build your building. Okay, from one layer to multi-layer, right? But this time, you need to try to connect your wires vertically. This is even more difficult because you need to try to make some holes, okay, in your wafer or substrate, right? Okay, you try to create some holes and you try to establish some elevator, right? Elevator from one layer to another, from A to C, A to D, right? So the processing will be more complicated. However, the performance, if it is designed well, the performance will be better. Because why? You can see here you have shorter wire. Okay, so shorter wire means your CPU will not be as hot when it operates, right? Because each wire here, you can think of it as a resistance. Okay, resistance will make very hard, right? Okay, after you play a game, your cell phone become very hot, right? You try to reduce that, so you make shorter wires. Okay, and after you play a game, because wire means energy dissipation. Okay, so after you play a game, no power, the power disappear, right? You try to make an IC with lower energy dissipation, so you can play your game longer, right? Okay, so you use 3D IC. So that's the point. Why we need to go from like a 2D to 3D packaging. Okay, and also some processing technique, right? Okay, so in the past generation, right, we try to use like UV light for the lithography. I will briefly talk about lithography like in the later part, okay? And now, as you know, like EUV is quite important because EUV you can achieve like a sub 10 nanometer lithography technique. Okay, before in the previous section, I said why TEM is important because it can achieve like a several nanometer resolution, right? And why only electron can achieve? Because if you use optical microscope, the wavelength is very long, right? The wavelength is long. Once you go to the nanometer scale, it's beyond the diffraction limit. You cannot see anything, okay? You cannot see anything. But for EUV, we try to use the wavelength very short light, okay, to do the focus. Okay, but there's some challenging. You can see that I remember there's a 9 or 11 reflective lenses in the EUV system. Why? Because at this wavelength level, you cannot find a glass lens to do the refraction. It's so so difficult to come up with a lens. It's not like you make your glasses and then you can do the refraction. Okay, so instead they use reflection instead of refraction. Okay, the difference. Okay, in Chinese we said 折射 and 反射. Okay, different. Okay, so you need to use the reflection. So this is very sophisticated. You need to tune the angle to make it work appropriately. Okay, so usually for this part we don't really say too much in our course. Okay, instead we need to invite some lecturers from the industry. Okay, so these are the companies that you usually see, okay, in the semiconductor industry. Okay, and most of the local students, okay, prefer these companies, okay, for the because they provide higher salary. Okay, and this year, okay, TSMC celebrates the opening of JASM in Kumamoto. Okay, I've never been there. Okay, but I've heard that many Taiwanese start to move there to find a job. Okay, so maybe maybe in the future I will visit there like sometime. Okay, so to conclude the first part, okay, the material science and engineering. Material science is to investigate the relation that exists between the structural properties. Okay, so the structure means, for example, if you think of carbon, okay, carbon can make into planar structure. Planar structure, you think of what? High conductivity, transparent, something like that. But if you make it very thick, it becomes not transparent. Okay, very thin, then transparent and high conductivity. Make it into nanotube, it becomes a semiconductor. Make it into a 3D structure, it becomes a diamond. Okay, also it becomes very precious jewel, right? Okay, and mechanical engineering is after we know the structure, we need to come up with a product, right? Product means if you want to come up with a Coca-Cola bottle, we need to make a mold. We need to know the processing temperature of the material in order to like do the hot pressing or to do the blowing. Blowing means you use the glass to like a balloon, right? You try to make it into the shape of the mold. Okay, after that, you need to do the demolding, right? So your material shouldn't stick to the mold. Otherwise, you will break apart just like what you've done in Wednesday afternoon, right? Some of them like break apart. Okay, and also we try to understand the material properties. Okay, that includes the mechanical, electrical, thermomagnetic, depends on the application of your product, right? Okay, so I think we can have a 10-minute break. How's that? Is it okay? Okay, we come back at 10 o'clock, and then I will spend 30 minutes to talk about some of the research. Some of my research, okay. I currently focus on the quantum dot and functional films for the optoelectronics application, okay. And these are some of the past research, okay. For example, I tried to make some nanowires on top of micropyramid. why I need to do that? Okay, because for this project, I work on enhancing the omnidirectionality of solar cell. For example, what's the omnidirectionality? For different place of the sunlight, we try to absorb the best um, efficiency. Okay, we try to achieve the best efficiency. So we don't need the solar tracking system. We don't need to like in the morning we change the direction to the left. In the afternoon we change to the right. We don't need that. Okay, because the nanowire here can what can induce some scattering of light, okay, to largely improve the overall absorption of the solar cell. But if you make it too high, okay, it will cause some defect. The defect here will lose the electrical performance of the solar cell. Okay, so there's an optimized length for these nanowires. Okay, and I try to incorporate some quantum dot to change the purple light or the UV light into the red light. Okay, to induce to increase the absorption of the solar cell. Okay, and so I also spent some time to did some like 1D nanowire devices, okay, or 2D atomic photo detectors. And also we try to use some like a 3-5 material, for example, the aluminum nitride or silicon carbide to make some harsh photo detector. Harsh means that your device is more robust. Okay, for example, if you try to put your device into outer space, there are large of radiation, particle radiation in the outer space. Okay, if you have, for example, if this is a space station here, okay, there are a lot of radiation. Okay, so you need to make your device more robust. Okay, so recently I will talk about two topics. Okay, one topic is the functional film for the display applications, and the second topic is the recent progress of semiconductor materials. Okay, so these are the difference of different displays. Okay, for LCD, we have a liquid crystal layer act as a switch. Switch is like by combining the liquid crystal with the polarizers. Okay, polarizers can allow us a light with a certain, we know the light is like a electromagnetic wave. Okay, so we have a certain direction for the electric field and certain direction for the magnetic field. So the polarizer can allow certain direction light passing through, right? And after it goes to the liquid crystal, it will change the electric field direction. Okay, interact with the liquid crystal and the electric field changes. Okay, and the we apply another polarizer on top. So if it change to like a 90-degree, okay, you will pass through. Pass through means you will see bright light. Okay, but if it does not interact with liquid crystal, it will stay the same, right? And 90-degree will block the light with the electric field in the 0-degree. Okay, so you will see dark image. Okay, so you can see that the liquid crystal here is a switch. Okay, and then by applying electric field on top and the bottom of the liquid crystal layer, we can change the orientation of the liquid crystal and change the interaction with light. Okay, so that's the mechanism of the LCD. And LED is like actively emitting material. Okay, by applying electrode on top and at the bottom, we can achieve light emission. And micro LED is the also usually made of inorganic material. Okay, and you will also actively emit. Okay, so you can see that LED needs like color filter because the backlight here is always white light. Okay, white light. So after passing through the color filter, it will become different color, right? And by combining red, green, and blue, you can achieve different color in your display, right? Okay, and these are some problems for the LCD. If you go to the shopping mall, you see a LCD, you can see that for different direction, maybe the light is different. Okay, I'm not gonna go into detail because it can take like 1 hour to explain that, but one problem here is that if you see from different direction, okay, especially for VA LCD, you can see bright image here, dark image here. Okay, so if you change your direction, you will see some weird patterns, okay, on your LCD. So this is what you see, okay. So at a different certain angle, you see different color performance. Okay, and one thing to adjust, okay, or solve this problem is we change the multi-domain. This is the orientation of liquid crystal. Okay, we change from one domain to multi-domain. Okay, multi-domain means that you can see half bright and half dark. Okay, so it will be similar to what you see in the center. Center here is gray. Okay, here is half white, half dark. Okay, however, by doing this, you need to like change from one direction to another direction. Okay, so you need more circuit. Okay, that means more cost, and also the transmittance of your display will be reduced because you need more circuits that will block your light. Okay, so the energy will be wasted. Okay, so another thing we can do is we try to apply a film that can change the path of light, okay, on top of your display to change to solve this problem. Okay, so you can see that there are different technique you can do. We try to make a film with a refractive index difference. Okay, so what can happen in this refractive index difference film? Okay, you can experience some diffraction, or you can experience some refraction, diffraction and refraction. Okay, because you have different pattern here. Okay, when the light encounters the sidewall due to the Snell's law, okay, it will be the direction will be changed, right? The direction will be changed. Okay, so the point here is we try to, let me go here. Okay, we try to change the path for the light going in this direction to large angle direction. Okay, that we can average the light difference in the large angle direction, and so that the difference between what you see in the normal direction and the large angle direction will be different. Okay, so this is the sum of the evaluation. Okay, usually we have a light profile going like this. Okay, the x-axis here is the angle. Angle is the viewing angle. You watch from the left, from the right, from the center. Okay, the profile is like this. After you try to use the film, it will be something like this, modified. So some part of the light will go to the large angle direction. Okay, so this is what we try to do in the design. Okay, and I missed this part. Okay, you can see if we try to evaluate the gray level, okay, from 0 to 255, okay, in the normal direction, you usually tune it to this scale. The scale here is usually called the gamma 2.2. Gamma 2.2. It means that this is exponential increase in the 2.2 power. Okay, but if you see, since there's some light leakage in the large angle direction, okay, if you go to like a 45 degree, you will become like this. This will cause this problem. Okay, this problem. So we try to make like a large angle. Large angle means off axis. Okay, to be similar to what you see in the on axis gamma. Okay, on axis gamma. Okay, so you can see after we try to incorporate our design, okay, normal view means you see from 0 degree, okay, and normal here means large degree. For example, 60 degree without any film, okay, it will be something like this. Okay, very different from gamma 2.2. But after you try to come up with the design, it will be more similar to the black line. Okay, that means the color washout problem. Okay, that what we see in the previous direction, the large angle problem, we call it the washout problem. Okay, will be solved. Okay, so by proper design, we are able to achieve high transmittance diffusing films with excellent oblique picture quality. Okay, but this also causes some problem. For example, if you add a functional film, you can see some image blur in the word here. There's some light coming out. Okay, why? Because you have large angle light encountering the sidewall here and achieve a total internal reflection. Okay, this causes some light coming out from the side. Okay, from the edge. Okay, and also some color dispersion problem. For example, here you have light here, but different color go to different angle, right? Different color go to different angle. So you can further to improve this by using different angular pattern. Okay, if you don't make it like a very straight, okay, you try to make a curve, this will be further improved. Okay, and for the second part, we try to incorporate some quantum dot to do light conversion. And the quantum dot here, I will skip this part, can be used to absorb the short wavelength light and then convert it into long wavelength light. Okay, so you still have a white light as a total, but now you can see the blue, green, and red are very pure. And then what can this do? If you have a very pure blue, green, and red light, okay, you can see this triangle becomes larger. This triangle becomes larger means the larger possible combination of your color in your display. So you can see that compare with OLED. OLED has not very pure green and red light. Okay, so compare with that, you can see that by incorporating quantum dot, you can achieve a better color performance in your display. Okay, but usually the commercially available, this is provided by the Samsung. Okay, commercially available quantum QLED are still using the LCD technology. Okay, LCD technology. So they simply change the backlight from white light to blue LED, and they add a QD layer here on top. Okay, to convert it into green light and red light. Okay, so you can see this is the performance of normal LCD, OLED, and the quantum dot. Okay, so this is an example of the film. You put it at the backlight unit of your display. Okay, so here, this is a QD tech roadmap. We are currently still at the first stage. Okay, we put the quantum dot, the rainbow color is the quantum dot film on the backlight unit. Okay, so in the front, you still have LCD, have polarizer, have color filter. Okay, the next stage is people will try to incorporate the QD onto the glass. Okay, and then the next stage, can we change the color filter to QD color filter? That means we need to do very precisional positioning of our QD conversion layer. Okay, instead of a film as a whole, we need to try to use like lithography or inkjet printing to print out the light conversion part. Okay, so but this can save your energy because for this, for the first two stages, the color filter is you can see the backlight here is still the white light, right? Okay, so the color filter here is to try to absorb the light you don't want, only allow the certain wavelength light to pass through. Okay, so it will lose much energy, right? But for this is conversion. Okay, for example, the blue light can directly pass through, but and the green light and red light, they use conversion to absorb the blue light and convert it into green light and red light. Okay, and the last stage is QD actively emitting device, and this is the most challenging because usually the quantum dot here is not quite stable. Okay, so if you For this, in addition to the light conversion, you also need to consider the electrical or the heat problems in your quantum dot layer. Okay, so this is quite challenging. We are still in the first stage. Okay, so this is the synthesis of quantum dot. Okay, at the first part of today's lecture, I said that the exfoliation of the graphene actually received the Nobel Prize, right, in like 2004 or something. Okay, and the synthesis of quantum dot also received the Nobel Prize last year. Okay, and how to come up with quantum dot? Okay, first of all, you try to come up with organic ligand with a precursor. The organic ligand can attach to the side wall of your crystal to prevent it from growing larger. Okay, the capping, we call it the capping ligand. The capping ligand with a charged long chain molecule. Okay, for example, if you have like a positive atom here, you will attach to the atom and prevent it from growing bigger. So first of all, we try to dissolve all our precursor into the solvent, and then we use after you mix them together, and then you heat it to a certain temperature, and then it totally dissolve, right? And then later on, you mix the ligands, okay, and also dissolve in the solvent, and then you try to use the best solvent, and you inject your precursor solution into the best solvent. So for best solvent, it will be precipitated, crystallized, right? You will see because it cannot dissolve, right? But upon the precipitation, your ligand will attach to the side wall to prevent it from growing bigger. So by tuning the concentration of ligand and precursor, you can achieve various size of crystals, okay? So this is how people can use. And the crystal size can change the emission wavelengths of your quantum dot and also the material. Okay, when you go to the bottom of the periodic table, you will have electron loosely bonded to your nucleus. Okay, so you will go to the red region. Okay, so these are the stability issue. People are still fixing that. And then this is what you see the quantum dot. At the outside here are long chain capping ligand. For example, they are like oleic acid and oleamine. Okay, oleic acid has a negative charge because it's like COO minus, and then oleamine has a NH2 plus. Okay, so positive charge, you will attach to the side wall. Okay, so prevent it from growing bigger. Okay, and these are some of our research. Okay, we try to come up with different. We mix with stereos nanocrystal and we do the vacuum filtration. We come up with different color conversion papers. Okay, color conversion papers. So you can see that under UV excitation, you can make it into different color film. Okay, different color film. And we try to use different halide ions, okay, to tune the emission color. Okay, and this is what you see in the past, right? And you use TEM to evaluate the size, the structure of the material. And we try to use some other cations to further improve the quantum yield. Quantum yield is how much light you absorb and how much light you emit. The ratio between them is the quantum yield. So the higher, the better. Okay, so we can further increase the quantum yield by incorporating some dielectric confinement. Okay, so I will not go into detail because due to time limitation, but this is quite interesting. Okay, so we have a blue LED chip. Okay, and we have a red film and green film. Okay, by combining these two, okay, we can add that one film, two film for each layer, right? Okay, we can tune the color of the LED. Okay, we can achieve because this blue, red and green, right? We can achieve white LED with different color temperature. Okay, and when you increase the concentration, what will happen? When you increase the concentration, it will become a continuous film. Large crystal. For large crystal, no light will come off. Okay, because the light needs the quantum confinement effect. You need to make it into quantum dot in order to make it emit. Okay, so for large crystals, no light, but it can be used to absorb light. Okay, it's the perovskite material is previously used for solar cell applications. Okay, and for this project, we mixed with cellulose nanocrystal to come up with a paper, and we try to make some electrode. Okay, so it can be used as a paper photo detector. Okay, paper photo detector. Okay, and because this is a paper, right, you can try to bend it. Okay, bend it like for 3,000 times and still retains a certain level of responsivity. Okay, so this is a brief summary of the first part. Okay, let me see how much time I have left. Okay, 5 minutes. Okay, for 5 minutes, I will try to go through some of the important topic in semiconductor material, but I will skip the first part. The first part is the physical explanation of the band gap. Okay, but for this, you can like, if you're interested, you can try to read it on your own, because I have some reference at the top, at the bottom. Okay, and this is the semiconductor device fabrication. This is what you do if you visit the TSMC. Okay, you will see something like this. If you try to come up with a like a electronic device, we need to make the patterning. Okay, the point for this is to pattern different region on the wafer. Okay, we start with the wafer. Okay? Originally, they're either like P-type wafer or N-type wafer. Okay, and we try to use some photoresist on top to do the patterning. Photoresist react with light, so we can have a certain region interact with light, certain region don't interact with light, so we can, after the exposure, we can remove the region that interact with light. Okay, and after that, we can do some etching. Etching means the photoresist here can protect the wafer from etching. Okay, but the region not covered by the photoresist will be etched away. So you can see the SiO2 here is gone, right? And you can also, other than etching, you can also do some diffusion or implantation. Like for example here, P, N, and what? And P, right? You can add another region here by ion implantation or diffusion. Okay, so this is just a simple illustration, but in TSMC, you need to like, after that, you need to define another region. So you need another mask, and then you need to do it all over again. So like for each device, you may need several hundreds of processing steps. Okay, several hundreds of processing steps. So these are the photolithography. Okay, for the photoresist, you can have either positive or negative. Okay, the only difference is for positive, the photoresist after exposure will be washed away. Okay, for negative, okay, the photoresist without exposure will be washed away on the development stage. Okay, so that's the only difference between them. Okay, and for photolithography, as I said earlier, previously people used DUV, okay, and now the EUV is a very important facility if you want to achieve high resolution processing, right? Because the wavelength here reduces to 13.5. Okay, and this is also another technology quite important, okay? Because as I said, when you go to very low wavelengths, short wavelengths, it's very difficult to focus. Okay, very difficult to focus to the certain point. Okay, so just one technology quite important is they use a drop of water because water has a different refractive index compared to the air, right? Okay, so they use water between their lens and their wafer to further improve the focus of their lithography system. Okay, so this is quite important. Before the EUV, people use this. And this is usually a very smart but risky step, okay? Because normally people don't want water on wafer, okay? But for this case, it becomes very successful, okay, to do the focus. And these are some photoreceptor systems. And also for etching, okay, if you have like, because we want to scale down, right? Okay, so if you have one periodicity, for example, this is 20 nanometer, okay, how to achieve 10 nanometer? Okay, this is called a lethal etch, lethal etch. That means we try, instead of doing only one time, after one time, we do another time. Okay, and after that, we can reduce the spacing between the structure, right? Originally 20 nanometer, but you do 2 times, it becomes like a 10 nanometer spacing. Okay, so the resolution can be largely improved. Okay, and this is reactive ion etching. Okay, reactive ion etching is we try to use reactive ions, or sometimes people say dry etching, okay, to react with exposed wafer. So we can come up with a hole at a certain region, right? And on top, the photoresist is for protection, okay, for protection. So if you have physical sputtering is for positive ions to bombard with your wafer, right? So the atoms in the wafer will be removed, right? And for plasma etching here, you have reactive materials reacting with your atom. This is like a corrosion behavior, okay? It reacts with your atom, so you will be take away, right, reaction. But you can see this is very collimated, okay? But poor selectivity, okay? All the materials can be moved away, but high anisotropy. High anisotropy is if I want to react with this region, we can very specific react with this region. Okay, for this, no anisotropy, you can react with all the atoms surrounding it. Okay, so no directionality. Okay, and very good selectivity. If you have a material you don't want it to react, okay, you can react only A material and leaves B material still on your wafer. Okay, but people usually combine with both. Okay, use this called the reactive ion etching. So we can tune the concentration of positive ion and reactive ion. Okay, so we can try to make better control of our structure. Okay, better control of the structure. Okay, and these are some techniques for thin film deposition. For physical, we have sputtering. We try to use ions to bombard with a target and then come up with a film on top of substrate. And we can do thermal evaporation. Is you try to use like a crucible, and this is like a loop. You can heat it up. This is like a resistor. Resistor, you can heat it up and you become vapor and deposit onto your substrate. Or you can use E-beam to heat it up, your material, to make it deposit onto your substrate. Okay, and for this, you need to have some magnetic field, because you see the electron here goes from the electron gun. Electron gun is when you apply a very high voltage to a filament, there will be electron coming out. Okay, and if you have magnetic field, what will happen? The direction of the electron will be changed. So you will bombard with your crucible with material, and then this will heat it up, becomes a vapor, and deposit onto the substrate. Okay, so, and also chemical vapor deposition is you have two kinds of material. After you mix the two kinds of gas, okay, it becomes solid material and deposit onto your substrate. Okay, so this is when you have chemical reaction, it becomes the chemical vapor deposition. For this, physical vapor deposition is only the bombard between the electron or ions, okay, ions. So for example, this is a metal organic chemical vapor deposition. We have 3-methyl gallium, right? 3-methyl gallium. React with what? Ammonium. Ammonium and then the 3-methyl gallium. React, you try to heat it up, your wafer surface. Okay, so when it reaches your surface, these two will react, right? And what will happen? Okay, nitrogen and gallium will react, becomes a gallium nitride film. Okay, and what do you get afterward? We have a byproduct called methane, right? Methane will be also a gas, right? The gas here will be evacuated. Okay, you try to use a pump to remove the byproduct. Okay, and for diffusion and ion implantation, for diffusion, usually you use like a gas with phosphorus atom. Phosphorus is a group 5 material, or boron atom. Boron atom is a group 3 material. Okay, if you have a silicon here, you try to provide a gas with like phosphorus or boron, you can make these atoms to diffuse. Okay, this usually requires high temperature because high temperature, the atom will diffuse into your silicon to make what? If eventually you have p-type material, you add more phosphorus, it becomes an n-type material. Or you can try to use some like group 5 ions. For example, gallium ions, or group 5 is like arsenic ions. Arsenic ions or group 3 ions, gallium ions, you try to provide an electric field. An electric field, it will like go to a certain point, right? Okay, and you have a mass here to block the unwanted ions, okay? So only the region near the center will be implanted. After implantation, you can also change p-type to n-type or change n-type to p-type, okay? But you can see the profile is different, okay? For diffusion, near the interface has a higher concentration. For ion implantation, it will reach a certain level in depth, okay? Certain level in depth. Okay, so this is the overall, you can see the 4 major processes. One is like photolithography, right? Lithography, deposition, and etching, and diffusion. These are 4 main steps. Combining together, you can have different type of order. Like first you go lithography, and then etching and diffusion, and then you go to lithography again, combines the whole semiconductor processing chain, okay? So I will skip the last part because I think the semiconductor processing may be more related to your visit to TSMC. And this is I already talked about this before, okay? FinFET and beyond. And this is also, this is a image from Samsung, okay? They provide I'm sorry, I don't have one from TSMC because usually they are highly classified, okay? So you can see they have those silicon films, metal gates, okay? So this is FinFET. And this nano electronics, maybe in the future, if I have time, I'll share with you. Okay, so I think I will end my presentation here. Enjoying your time in Taiwan, and there's maybe you don't have time to go to Taipei Dome, right? Because at that time, okay, the Taipei Dome opening on March, right? And Yomiuri Giants visit Taiwan, okay? And I'm a fan of Brother Elephants, the Taiwanese team. Okay, but unfortunately at that time I was in Japan. Okay, I was in Tokushima, so I can only show this slide. I cannot go to the Taipei Dome. Okay, and you can maybe next time you can come in the end of the new year, you can see the Taipei 101 blowing up, okay, by the fireworks, okay, and then if you have time, you can take some time to visit the Ximending and night market, okay. So yeah, that's all of my presentation. Thank you. Okay, let me check whether the next any question. No question, right? Okay, very good.